We've already gotten a little bit of preview for semi-log plots, which is the topic we're covering in topic 2.15. So earlier this unit in topic 2.9, we looked at the idea of using a logarithmically scaled axis to help us better understand data that is exponential. This is a legitimate type of data that engineers use to look at wide-ranging data in a very useful way, so you don't have to scroll or you don't have to get rid of beginning data. We'll now return to this idea to examine it in a little more detail with an entire lesson over semi-log plots. So in a semi-log plot, one of the axes is logarithmically scaled. I'm going to stutter over that word this whole time. In AP Pre-Cal, we will only be scaling the vertical or the y-axis. In reality, you can logarithmically scale either axes or both axes at the same time. In engineering, that's called a log-log scale, which is kind of fun to say. With a semi-log plot, so half-logged, semi-log, so it's only one of them, where the y-axis is logarithmically scaled, this is a huge idea for today. Exponential functions will appear linear. Highlight that in some color for yourself and put 2 exclamation points next to it. This is huge. So let's see what this looks like in reality. In this first example, example 1, after Mr. Passwater, who's the person who wrote all of your notes, he's awesome, tells another one of his hilarious math jokes, it begins to spread around the school. The number of people, P, that have heard the joke after T minutes is graphed on the semi-log plot above, where the vertical axis has been logarithmically scaled. What I want us to do is when we notice a y-axis has been logarithmically scaled, meaning you see it is not evenly distributed like a typical Cartesian plane, I want us to highlight that axis. That way we notice we're not counting by 1s, 2, 3, like that. We're counting in powers of 10, because this is logarithmically scaled with a base 10. Do y'all remember how to read these graphs? Yeah, we did really well with this the other day. Cartesian plane is the one you've been using since forever, where it's x, y, and everything is even. So it goes, you're counting by 1 each time, and then counting by 1 each time, or counting by 5, and counting by 10. It's even. That's a Cartesian plane. That's a great question. I assume the person who created or codified it, his last name was Cartesian, but I don't know. I will Google that for you. Thank you for asking. So the question here is use the features of the semi-log plot above of the data modeling Mr. Passwater's joke's popularity to justify why an exponential model is appropriate for the data. So similar to the lesson when we talked about whether a residual graph showed it being appropriate for the data, we can make a similar argument here. Do you notice that on this graph here, this data appears linear? Great. Our spidey senses should be going off because on a semi-log plot, if something shows up linear, that means in all actuality, it is an exponential function. If we were to graph this on a regular Cartesian plane, it would show a curve like we're used to seeing for exponential data. So our argument here would say something like this. The semi-log plot above appears to be linear. You guys notice that it appears to be linear. So the exponential model is appropriate for this data. A similar kind of argument or reasoning we were giving in the lessons about the residuals, where the residuals showed no pattern, so the model is appropriate for the data. This is the similar kind of argument. It's just in a semi-log plot, we can see that things that are linear come from exponential data. So if we see a linear function, we knew it came from an exponential regression, exponential data. Example number 2 goes on to still use this graph. It says, which of the following functions could be a model for P? Remember, P is modeling the popularity of Mr. Passwater's joke. First things first, we already said it should be exponential. Can we get rid of a couple answer choices that are not exponential functions? Yeah, which ones? We're going to get rid of A and we're going to get rid of C. The A is what kind of function? Linear. And C is what kind of function? logarithmic. That's not what it's going to be because we are modeling an exponential function here. After this, we need to look at the data from the table to see what the coordinate points might be so we can match it up. If you guys were going to read this coordinate point right here to me, what would be that coordinate point? 0, 2. Very good, which means we have an initial value for our exponential function at 2. When we look at initial values for exponential functions, remember, exponential functions are a times b to the x power. Is a or b your initial value? A is your initial value. Out of these two options, out of b and d, which one has an a value of 2? D. What is this a value right here? Is there a number there? Which means the a value is 1. This one, we can see the a value is 2. So D is probably the exponential function that models this data. And this function is telling me it doubles over time, which if you created a table of all of the values, you could see that this doubles every time. This is at 2, this one's at 4, this is at 8, and then probably 16, and then close to 32, and then 64. We're doubling every time, which is why the 2 is the base of this exponential. Now, when we logarithmically scale the vertical axis for a semi-log plot, we are not changing the actual y values. To logarithmically scale the vertical axis means that we are taking equally spaced values on the y-axis that are proportional to each other, whereas the equally spaced values on the x-axis are linear. So we're still modeling linear inputs and proportional outputs, which is our definition of an exponential function. So in example 3, it gives you a table, and it wants you to figure out which of the following plots which of the following graphs could represent these data from the table in a semi-log plot where the vertical axis is logarithmically scaled. Again, we're looking for the vertical axis, up and down, to be log scaled. There are 2 examples on here that we should be able to get rid of right away that are not logarithmically scaled on the y-axis. Which 2 can we get rid of? The first one. This first one, if we look at its y-axis, that is counting by an even value. I know it has those bold lines it's trying to trick you, but look at what the actual values are. Every bold line is going up by 0.5 each time. So that is not logarithmically scaled. But if we look at the second one, we go from 1 to 10 with proportionally spaced values each time instead of evenly spaced on the y-axis. That one's okay. The third one, you're right, is not good. I guess we could mark these guys off. We're going to put like no underneath them. The third one is also equally spaced on the y-axis instead of proportionally spaced, so we don't want that one. The last one, though, is logarithmically scaled because we can see it is proportionally scaled with base 10. The question now is, which one of these better represents my data? If we look just at the first value, which is 1, 40, does this point represent 1, 40? No, that's like 1, like what, 0.7? Does this one represent 1, 40? Yeah, that's a much better telling of the graph. So this one's a no because of the coordinate points not actually matching. But this one right here would be the best representation of this data in a semi-log plot. We see that the axes are scaled how we want. That's the first thing we look for. And then we look to make sure the data is appropriate, that it has a correct coordinate point. Make sense? Okay, here's another practice. We were really good at this the other day, so I just want you to practice. I want you with your markers, if you are a colored marker person, I want you to plot these points for me just to get good practice in, to see if we remember how to plot these points. Again, y'all were real good at this when we did it the other day, so I'm going to stop talking. I want to see what you can do. Okay, let's check how we did. For letter A, 0, 200 would be approximately here. How'd you do? Yay. For B, 1, 25 would be approximately here. How'd you do? Fabulous. Okay, 2, 7. 1, 2, 3, 4, 5, 6, 7. Here? Did I count right? Nice. For D, 3.2, we want to make sure we're accurate here. If you notice, in between 3 and 4, there are just a few tick marks, which means this is 3.2, 3.4, 3.6, 3.8, and 4. So on 3.2, I'm going to go up to 800, 100, 200, 300, 400, 500, 600, 700, 800. Did y'all get that there? Hooray. And then for the last one, 4.6, again, 4.2, 4, 6 would be here, and then 1.5 would be approximately, boop, right there. Yeah. How'd we do? Great. Fabulous. So remember, the first line is not 0, the first line is 1. So 1.5 is just in between the 1 and the 2 line. Fabulous. I feel really good about semi-log plots, don't you? So let's talk about how we can write equations that represent these linear functions on these semi-log plots. So as we have seen, if we graph an exponential function on a semi-log plot, the graph will appear linear. That's our huge idea for today. In these cases, we can create a linear model for the graph on the semi-log plot. So follow along with me because there's some color coding here that I think might be important, and I'm going to put colors on colors, and it gets a little crazy, so follow along with me. Given the exponential model, a times b to the x, the corresponding linear model for the semi-log plot is given by y equal to log base n of b times x plus log base n of a. Whoa. First of all, what's going on here? Great question. This is a linear model. In Algebra 1, when you wrote linear equations, what's the form of the equation you use the most? Oh, snap. So y equals mx plus b. We're writing the same kind of function. However, the slope is not represented by the fraction m anymore. It's represented by the logarithm of n, logarithm base n of b. The y-intercept, which confusingly is using the letter b, it's not the same b, it's your y-intercept, is represented now by log base n of a. Now, where did these come from? I'm so glad you asked. Here's where we're putting colors on colors. Your b value that you're plugging into that logarithm comes from here. A times b to the x. That's the b you're grabbing. That's the b you're using. The a in this logarithm, log base n of a, is coming from this a, your initial value of your exponential function.
What's that, green?
Yeah. So the slope of our linear function is this pink, log base n of b, where b is the green value from your exponential. And the y-intercept is log base n of a, where a is the base from your exponential function. Just kidding, is your y-intercept, I said that backwards, from your exponential function. By the way, note number 2, the n that we're using corresponds to the base used for the scaling of the vertical axis. So 9 times out of 10, n is probably going to equal 10, so that we're using a common logarithm. That is not always the case, but it is the case in most questions I've seen at the level of this course. In real life and engineering, it's whatever base you're using, maybe E. Wild. So a question you may see would be something like this. It says the semi-log plot above corresponds to the data for the table in example 3 that's on the front of your page. Write an equation for the linear model of the semi-log plot of the form y equal to log base n of b times x plus log base n of a. We need the values of a and b for this exponential data to make this happen. Here's how I want you to do it. In a problem that doesn't have a table that goes along with it, you're going to read these coordinate points and use them for stat edit. However, we have the table from example 3 to actually see the data points. So what I want you to do right now is flip your paper over, go to stat edit on your calculator, and type in the table from example 3. It's the one that has x values of 1, 2, 3, 4, and 5, and f of x values of 40, 60, 90, 135, and 203. Go ahead and do an exponential regression for this data. As a reminder, exponential regressions are option 0 on your stat calculate screen. In this problem, because we are not at the end of the problem, we don't want to only write down 4 decimals. We round at the end of a problem. Your calculator does not store the little a, little b in a way that's easy for us to grab. So when we're writing this problem down for ourselves right here, I'm just going to go ahead and write literally every single decimal that shows up on my screen because I want to use the most accurate number possible and round at the very end. So I'm going to write 26.6403745, the whole number I see on my screen. Is that the number y'all got? Uh-oh. Times 1.500740001 to the x. That is the exponential function that is modeled in that data. Which means for us that the a value for our problem that we're going to use is all of this business. That's going to go right there. And the b value we're going to use is all of this business. And we're going to put that right there. So again, we don't want to round the number in the middle of a problem so we can have the most accurate final answer as possible. That's why we store a lot of these values in our calculator. It is stored in your calculator, but not in a useful way for us in this problem. So if I was trying to write the linearization of this data, meaning the line that represents this straight line through the data, we would write y equal to log base 10. Why did I choose 10, by the way? Well, it's common, yes. Look at the scale of my axes right here. What's the base I'm using here? 10. Okay, that's why I chose 10. So log base 10 of b, 1.500740001, multiplied by x plus log base 10 of 26.6403745. That's a lot of numbers. Good thing we're almost at the end of this problem because now I can find the slope and the y-intercept for this data by just typing log base 10, which is your common log, special button on the front, log of 1.500740001. And if I do that on my calculator, I get a slope of 0.1763. This time I am rounding, because this is the final step of this problem, x plus log base 10 of 26.6403745. Oof. Which is 1.4255. Binary would be only ones and zeros, by the way. So again, all I have done is taken the parentheses slope right here, log base 10 of the number we got for B, and I evaluated that in my calculator to get the slope of this line. Then I took log base 10 of the initial value from my exponential function, and I got the linearization's y-intercept.